Hello and welcome to section 10.7. We're looking at vector functions and space curves. So let's first define what a vector function is. Okay, so we'll define a vector function to be some function whose domain is some set of real numbers and whose range is a set of vectors. So it's some function that takes a real number input and takes it to, for example, R2, or we'll look at functions that take a real number and bring it to R3. So one of these cases is generally what we'll be looking at. So we might define a vector function like this, r of t. So t is the variable in the real numbers, and then the three components of this happen to be f of t, g of t, and h of t. Of course, if it was just a two-dimensional vector, you'd just leave off the h of t, which could also be written f of t times the I vector plus g of t times the j vector plus h of t times the k vector. Okay, two ways of just kind of denoting this idea that you have really three functions, one for each of the dimensions, and each of these functions is a single variable function. Here's an example. We have this vector function r of t is t cubed for the x component, natural log of 3 minus t for the y component, and then square root of square root of t for the z component. And so the domain here is going to be, let's see, well, we need a couple of things. We need t to be greater than or equal to 0 because of this, but we also need 3 minus t to be strictly greater than 0, which means t has to be less than 3. And so the domain is going to be from 0 up to 3, non-inclusive, the 3. All right, so we'll define the limit of a vector function as t approaches some value a. It'll be what we do is we just take the limit of the three components. So that's how a limit is defined. Perhaps this is exactly what you would expect it to be. And this is only going to be true if these limits exist. If they don't exist, then the limit of the vector function doesn't exist. Okay, so here's an example. Let's try to evaluate this limit of r of t as t goes to 0, where you have these, the components, the first component's 1 plus t to the third. So this limit is going to be, for the first component, it's just going to be 1, because for the first component, this is a polynomial, so the limit as t approaches 0 just is going to be the value when you plug in 0. For the second one, it's continuous, so you can actually plug in 0. It's going to be 0j. I'll write it out even though it's 0. But for the next one, do you remember this limit, the sine of t over t, the limit of that is 1k. So this, you could write it like this. You could write it as 1, 0, 1. So this is the limit of this function. So in a sense, you can think of it as this is the point in 3D space that this function somehow is getting closer to, or this is the vector that this function is approaching as t approaches 0. Okay, so we'll define continuity for vector functions in the same way we do for single variable functions. We say the vector function is continuous at a if the limit as t approaches a of r of t is equal to r of a. If you think back, this is exactly how you did it back in Calc 1. This is just, we're just have to extend these definitions. So if you have three continuous single variable functions, f, g, and h, and they're all continuous from the same interval I for like values t, then we call this set of all points, we'll call it the set C of all the points of all the x, y, z points, where x, y, and z are all determined by the functions f of t, g of t, and h of t respectively. Like, so for any value t, you plug it into f, g, and h, and what you get is three values, and those make your x, y, and z coordinates. We call this a space curve. Okay, and so we'll call f, g, and h the parametric equations of C, and t is the parameter of these parametric equations. Okay, let's take a look at this vector equation. So if we want to think about what is the curve that's going to be given by, defined by this vector function, what we have is this f of t is 1 plus t, which is a line. Then we have g of t is 2 plus 5t, which is another linear function. And then h of t, negative 1 plus 6t, also a line. And so it follows as t increases bit by bit by bit. Think of it. You would go from when t equals 0, you'd be at the point 1 to negative 1. When t equals 1, we'd be at the point 2, let's see, 7, and then we'd be at 5. And then when t equals 2, we'd be at the point 3, and then we'd be at 12 for the y, and then we'd have 12 minus 1, 11. And so what we have then, if you were to graph this out in 3 dimensions, and if you graph it out, you see indeed, yes, this is a line in 3D space. Okay, so this is what a line would look like. And of course, we already know that, right? We know how to define the equation of a line. Okay, so let's take a look at this one. Now, for this vector function, or we want to think about the curve that's generated by this vector function. So for the x and the y components, we have cosine t and sine t. So if we were just going to graph like x equals cosine of t and y equals the sine of t, in the xy plane, it's just going to look like this. It's just going to be a circle as t increases, right? It's going to go around and around and around. But z is equal to t. So what you want to now think about in 3-dimensional space, it's not, although in 2D it would be a circle, right? That would be the base of this thing. In fact, what we're going to see is I'm going to do my darndest to try to illustrate the 3-dimensionality of this thing. So where we're starting at, this is t equals 0, and once we get to t equals 2 pi, we should at least it should look something like this. We've kind of gone up around this corkscrew, and actually down below we should have a similar thing happening where we go around. Okay, so it's kind of like a spring. Now it's hard to see in drawn as a 2-dimensional object, but let's just see what this looks like. Yep, yes indeed, it's a what we call a helix. All right, let's look at this example where we wanted to find the vector equation for the line segment joining P and Q. I think we already saw that we could do this in a couple of ways. What we can do is write this as R of t we can have it be, let's see, t times the vector 2 minus 1, 3 plus 1 minus t times the vector 1, 3 minus 2, where t is going to take values from 0 to 1. This is one way of connecting 2 points, and actually I could have swapped the 1 minus t and the t. Either way it would work. Let's just expand this out and see what this is. We have 2t, negative t, and 3t for the first vector, plus 1 minus t. Then we're going to have 3 minus 3t, and we're going to have minus 2 plus 2t, just being careful about the negative 2. Now adding these two things together, for the first component we're going to have 1 plus t. For the second component we're going to have 3 minus 4t. And for the next one we've got, let's see, minus 2 plus 5t. So here we have our vector equation. And if we wanted to put this in terms of the parametric equations, so here they are. We have f of t is 1 plus t, g of t is 3 minus 4t, and then h of t is negative 2 plus 5t. So those are the parametric equations, and then up above those, that is the vector function. They represent the same curve in space, which is a line segment. And that's because, of course, we've restricted the values of t to be from 0 to 1. So here we want to find a vector function representing the curve of intersection of the cylinder x squared plus y squared equals 1, and then the plane y plus z equals 2. And graphing it out, this is what this looks like. You can see the cylinder is going up on the z-axis. The plane is at this kind of tilt, so they intersect with an ellipse in 3D space. So we're going to find this equation, and the way we're going to do it is we have to start parameterizing variables, right? And so what's going to be useful is to take the x squared plus y squared equals 1 and just start to parameterize the points, where we're going to say, okay, for all of the points on this, x is going to be the cosine of t and y is the sine of t, right? Because the excuse me, the cylinder, all the points on the cylinder are going to be on this circle, so for some value of t. And so we're going to that'll take us around the ellipse, but we need to figure out the z value. And because y plus z equals 2, we can solve for this. Z equals 2 minus y, and we're going to instead actually write z equals 2 minus the sine of t. So then these become these become the three equations, the three parametric equations. We can write it like this. So a vector function would look like this. R of t equals cosine t, comma, sine t, comma, 2 minus sine of t. So that's the vector function representing that intersection of those two surfaces. Here's an example of one that you would never guess what it looks like before graphing it. So you have this kind of spiral that goes in a ring. And then here's another example. Okay, so if x is 2 plus cosine of 3t over 2 times cosine t, and y is 2 plus cosine of 3t over 2 times the sine of t, and z is the sine of 3t over 2, here's what this is going to look like. So this kind of squiggle that goes around in 3D space. So you can see you can generate a lot of strange curves in space using these vector functions and parametric equations. Okay, so we're going to define the derivatives of vector functions, and we're going to kind of blast through Calc 1 with these vector functions. And first, the technical definition. So the derivative of a vector function, which will denote r prime, or dr over dt, is going to be defined as this difference quotient limit. So the limit as h goes to 0 of r of t plus h minus r of t all over h. Now we're not going to be doing these limits in practice because the derivative is going to, these limits are as we already said, it's a linear operator. So like it's going to apply to each of these components of the vector function individually. We can actually just take the derivative of each of the components. Okay, so r prime is going to be, we're going to call it the tangent vector at point P, and where P is like the point given by position vector r of t. Right? You can convert from position vectors back to points, and but that's only going to be the tangent vector as long as this derivative exists, and as long as it isn't the zero vector. In practice, in 3D space, what you'll find for these continuous functions, the tangent vector is not going to exist only when the kind of this curve that goes through space comes to a point and then makes a complete 180-degree turn and comes back. If it can stop moving in one or two of the dimensions, but if it stops moving in all three dimensions and then makes a turn to a different direction, that is going to give you a 0 for the derivative. So the tangent line to the curve C at point P is a line that is parallel to r prime, and it passes through point P. It's exactly what you think it would be. And then the unit tangent vector, which we'll call capital T, is just that you take the derivative r prime and divide it by its magnitude, just as you would with any vector, to turn it into a unit vector. That's going to be called the unit tangent vector. This capital T, this unit tangent vector, is going to be important for a number of reasons, but we'll be seeing those shortly. Okay, and here's the theorem that I alluded to earlier, that if you have your vector function where the f, the g, and the h are all differentiable functions, then the derivative, r prime, is going to be given by, well, each of the components is going to be just the first derivative of the corresponding single variable function. And so finding the derivatives in practice is just a matter, it's just the same stuff, it's just finding derivatives of single variable functions. You just have to do it 3 times. So let's take a look at this example. So we can express this using the basis vectors or in the component form. Either way we should be comfortable doing. So let's say I have this vector function where we have 1 plus t cubed I plus t to the minus 1 j plus sine of 2t k. This is one we looked at a little earlier. Now the first derivative, r prime, me saying first derivative already gives you a hint that we'll be taking higher derivatives later. But anyway, I'm going to show you it's just a matter of taking derivatives, right? So 1 plus t cubed, the derivative is going to be 3t squared, and then times the I vector. Now if this one, t times e to the negative 1 is just going to be e to the negative 1. The e to the negative 1 isn't anything special other than it's just a coefficient. So don't get fooled. Now what is this derivative of the sine of t? It's the cosine, or sine of 2t, but by the chain rule, remember, we have to then multiply this by 2, and then we have this times k. So this is our our derivative, r prime. But if we wanted to find, let's find the unit tangent vector at let's say at 0. Okay, so what I want to do is I want to evaluate this r prime at 0, and I'm going to put it in components. So it's going to be 0. It's going to be I'll write it as 1 over e because that's maybe a little cleaner looking. And then the cosine of 2t, do you remember what the cosine of 0 is? The cosine of 0 is 1, so it's 2 times 1 is 2. So this is not a unit vector. What I need to do is find its magnitude, okay, find the length of this vector. So it's 1 over e squared plus 4. And so the unit tangent vector, when t is equal to 0, would be given like this. It would be 0, it would be 1 over e times square root of 1 over e squared plus 4, and then 2 over square root 1 over e squared plus 4. Not particularly pretty looking, but it is a unit vector. It has a length of 1. Okay, let's take a look at this one. Let's find the tangent line to this helix given by x is 2 cosine t, y is sine of t, and then z is t at the point 0, 1, and then pi over 2. So what I want to do is first, well, I guess I have to do 2 things. One, I have to figure out what is t, because I'm given the point, but I have to figure out what t is. And the first 2 components, it's not obvious, perhaps, but actually for the third, the z, since z is pi over 2 and z equals t, that means t is actually pi over 2. Okay, so that's what I'm going to be using. Let's find the derivatives. The derivative is going to be r prime of t is equal to, the derivative of 2 cosine t is going to be negative 2 sine of t. Remember how to take derivatives of cosines. You get a negative sign. And then the derivative of sine of t is a cosine t. And the derivative of t is just a 1. And so I need to now take this derivative, evaluate it at pi over 2, and what I'm going to get is, so remember, what's the sine of pi over 2? That's 1. So I'll have negative 2, and then cosine of 90 degrees is 0, and then 1. So this is my tangent vector. Okay, to find the tangent line, I have the point 0, 1, pi over 2, and so my tangent line can be written as x equals 0 minus 2t, y equals 1 plus 0t, and z equals 1, I'm sorry, pi over 2 plus 1t, which can be cleaned up quite a bit. This is just minus 2t, this is 1, and this is pi over 2 plus t. So here's my tangent line given by that, which we could also express as a in a vector equation as well. But anyway, that I'm happy with that. Now, rather than rewriting all of these, I'm just going to copy this from my notes. We've got if you have u and v are two differentiable vector functions, c is a scalar and f is a real valued function, here are some properties that we have. So first off, we've got a sum rule. So the derivative of the sum of two vector functions is going to be the sum of the two derivatives. You can take derivatives separately. The derivative of the scalar multiple of a vector function, like multiply a vector function by a scalar, is going to be, you take the scalar, you can factor it out, and just it's a scalar times the derivative. Okay. Now, if we have a single, the next one, if you have a single variable function times a vector function, the derivative of that is going to follow a product rule. So check this. So it's going to be f prime of u plus f times u prime. So this is like the product rule. That's the first product rule. So the derivative of a dot product is going to also follow a product rule kind of formula. So the derivative of u dot v is going to be u prime v dot v plus u dot v prime. And then the third product rule is for cross products and actually follows the exact same pattern. The derivative of a cross product of two vectors is going to be the derivative of the first, u prime cross v plus u cross v prime. So three product rules for three different kinds of multiplications: scalar product, dot product, and cross product. And lastly, what we have is a form of the chain rule. A vector composition of a vector function inside that f of t, some scalar real valued function, right? You're going to have f prime of t times u prime of f of t. So this is like a chain rule. All of these they kind of follow exactly what you imagine they probably would. They work out just kind of like they did in single variable calculus. So we're going to use this fact to make this proof that if the absolute value of r of t is equal to c, so some constant, so if no matter what value t is, that the vector's magnitude is always constant, that its first derivative, the tangent vector, is orthogonal to the position vector for all t. Okay, this is what I want to do. So if the magnitude of the vector is c, the magnitude squared is equal to the vector dotted with itself. And you can, if you don't remember this fact from earlier, you can verify this pretty easily. What I want to do is take the derivative of both sides. So take a d over dt of both sides. So I'm going to get 0 equals, by the chain rule, it's r prime of t dot r of t plus r of t dotted with r of t dotted with r prime of t. So in fact, what this tells me is 2r prime of t dot r of t equals 0. I'll put my arrows up top so that I don't get in trouble, which means that, well, the dot product is 0, so r prime and r are orthogonal. If the dot product of two vectors is 0, then that means they're orthogonal. That's it. Okay, so the definite integral now we'll define for a vector function, a continuous vector function. So we're taking a definite integral for where t values go from a to b. The integral of r of t from a to b is going to be found by just taking the definite integral of the three component vectors, all of them from a to b, component functions, f of t, g of t, h of t respectively. So it's just going to be three integrals. They're not interacting with each other. It's just you integrate f, integrate g, integrate h. So the fundamental theorem of calculus for vector functions can be written like this. The definite integral of r of t from a to b is going to be capital R of b minus capital R of a, where capital R is the antiderivative of r, meaning if you take its first derivative, you get r. Okay, so here's an example where I want to find the definite integral of this vector function. It's another helix. So we have 2 cosine t I plus sine of t j plus 2t times k vector. So the integral is going to be found by integrating these three components, which we could do. We just need to, we could do it a couple ways. We could just write it in these components, so 0 to pi over 2 of 2 cosine t dt, integral from 0 to pi over 2 sine of t dt, and then we have integral from 0 to pi over 2 of 2t dt. So we're just going to evaluate these one by one. Okay, so for the first one, the integral of the antiderivative is the sine of t. It's going to be the 2 sine of t, right? And we're going to evaluate it from 0 to pi over 2. For the next one, the antiderivative, it's negative cosine of t, and evaluating it from 0 to pi over 2. And for the third one, it's going to be t squared. Remember that? 0 to pi over 2. And now I'm going to evaluate these all one by one. So the first component, 2 sine of t, let's see, the sine of pi over 2 is 1. That's going to be 2 times 1 minus 0. Okay. Then we'll have negative, what? Negative, let's see, the cosine of pi over 2 is 0, and the cosine of 0 is 1. 0 minus 1, like that. And the next one, it's going to be pi over 2 squared minus 0. Okay, so let's just finally write everything out. 2 times 1 is 2, negative 1 is 1, and then we have pi squared over 4. That is my definite integral of this vector function. So you can see it's really just you take the integral of each of the three components separately and independently of each other, and then you just put them together in one function. So what we're doing here is nothing but single variable calculus, but we just do it 3 times. Okay, now let's take a look at this. We have two space curves given by these vector functions, and we want to find the angle of intersection of the two curves at the origin point. And so what we're going to do is we're going to find the tangent vectors. So let's find r1 prime of t first, and then we'll find r2 prime. So for r1 prime is going to be the derivative of t is a 1, derivative of t squared is 2t, and the derivative of t to the third is 3t squared. And r2 prime of t is, okay, the derivative of sine of t is going to be cosine of t. The derivative of sine of 2t is going to be 2 cosine of 2t. Remember that chain rule. And then we have the derivative of t is a 1. Now I need to evaluate r1 prime at 0 because at the origin t is equal to 0. That's the only way to get that for the first point, actually for the other one as well. So it's going to be 1, 2, 0, 0. And for the second one, r2 prime at 0 is going to be, the cosine of 0, remember, is 1. 2 times the cosine of 0 is 2, and then we have a 1. So we have to find the angle between them. Remember, the angle between them is the cosine inverse of their dot product. So it's 1, 0, 0 dotted with 1, 1, 2, 1 divided by the magnitude of the 1, 0, 0 vector, which you probably already realize that's a 1, and the 1, 2, 1 vector. Okay, let's actually evaluate these in another step. Cosine inverse of, so what's the dot product? It's 1 times 1 is 1, and then the other products are all 0. So it's 1 over. We have the first vector has a magnitude of 1, and the second one has a magnitude of 1 squared plus 2 squared is a 4 plus a 1 squared. It's 1 plus 4 plus 1 is 6, root 6. The cosine inverse of 1 over root. This comes out to 65.9 degrees. That's the angle of intersection of these two. Okay, let's look at this example. Two particles are traveling along these two curves that are given by these space curves, given by these vector functions. So if R1 is t squared t to the third, which we just looked at in the previous example. And then R2 is given by 1 plus 2t, 1 plus 6t, and 1 plus 14t. So we have a line. So we first want to ask, do the paths intersect with each other? Like at time t1 on the first curve, and maybe at t2 on the second curve. So what I'm going to do is actually I'm going to replace the t's in the second equation with like s's. So what I'm going to do is set the first component t equal to 1 plus 2s. I want to see if there's a time when on the second curve it comes to the same place where at maybe some other time t on the first curve it was. Let's set t squared equal to 1 plus 6t, and then t to the third equal to 1 plus 14. I'm sorry, I put a t. I want that to be an s. All right, let's see if we can figure this out. Well, what does this mean? For the first one, we can actually replace that 1 plus 2s in for t, and then we're going to get 1 plus 2s squared equals 1 plus 6s. In other words, 1 plus 4s plus 4s squared equals 1 plus 6s, which is a quadratic 4s squared. We have minus 2s equals 0. So in this case, we would have, if we factored out the 2s, we'd have 2s minus 1 equals 0. So what we get is, let's see, we have s at s equals 0, and when s equals 1/2, we get a point where the first component, what does that mean? If the corresponding t would be for the 0 would be 1, and the corresponding t would be t equals 2 for the second one. What I'm doing is I'm plugging 1/2 in for s in this first equation. I guess what we need to do then is check and see whether, so what we have now is two solutions that satisfy the first two coordinates being the same, but we have to check and see in the third component if that's the case. So let's plug the first one in. Let's see, is 1 to the third equal to 1 plus 14 times 0? And then in Eureka, we've got it, like 1 equals 1. So yes, the two paths do intersect. I'm sorry, the paths intersect, yeah. Now, the second question is, do they collide? And that one's a little easier to answer. We can ask, is there any time when t equals s that's going to satisfy these two equations? And we've actually answered that right here. The only way to satisfy the first two equations simultaneously is for s to be 0 and t is 1, or s to be 1/2 and t equals 2. There's no value of time for both s and t where they're in the same spot. So actually, no, the two paths don't collide. The two particles don't collide, right? The particles come to this point at two different times. And so, yeah, the particles do not collide, but the paths do intersect. Okay, well that covers this pretty long section on vector curves. So it's a lot to take in. or vector functions, I should say. But anyway, we'll get some practice and you'll become a master of this, just like everything else. All right, bye.